Welcome back, everyone. In this lesson, we're going to create the ability to call a sum function from C. So the core of our program will be the C program. So let's start with that. We're going to create a new file called csum.c. And we're going to include stdio.h. Can include sclib.h, and here we're going to say init main, init argc, char argv. We're just going to return 0, and now here we're going to put our prototype for our sum function. So we're going to say init sum, init x, init y, and you'll notice we don't declare anything in here. That's because that'll be our assembly that implements this function. Okay, our assembly will implement it. And now in here, we're just going to say init result equals sum 50 and 20. So the result should be 70. Yeah. And we're just going to say printf sum 50 plus 20 equals, and we're going to do %i result. So that's our C program done. Now we need to make the assembly program that implements this sum. So let's try that now. We're going to create a new file. We're going to call it csum.asm. We're going to say global sum because we want to actually export that function that we're about to create. And we're just going to say bit 64 at the top here so that it's 64-bit code. And here we're just going to say sum colon move rax rdi because rdi is the first argument. I'm just going to put a little comment here so that you know. So that's RDI, that's RSI. And then we're going to say add RAX, RSI. So that will add RAX and RSI together and store the result in the RAX register. So then we just return. So obviously, all C programs expect the return value to be in the RAX register. Okay. So we know that the add instruction will set that RAX register, okay? Because it'll add RAX and RSI together, store the result in the RAX register, okay? Simple. So that's our assembly program also done. So now we just need to actually compile it. So what we're going to do, we're going to say nasm-f elf64 csum.asm-o csum.o. So that'll assemble the csum ASM file into a 64-bit ELF format. Now we just need to compile it and link it with C. So we're going to say gcc-o0 to turn optimization off, -wall, and we're going to say csum. In this video course, you're going to learn how to build your very own multitasking 64-bit long mode kernel. And it's even going to support graphical user interfaces. Yes, that's right. You will be able to load calculator applications, images, and a nice GUI with a Windows system. All that's going to be done in this course. Even UEFI is supported. You have to watch this. We even use PCI, and we even create an NVMe disk driver, which will allow you to load sectors from your SSD disks. In the module 1 of the course, we focus on taking 32-bit kernel that we made in the part 1 video course called PeachOS, and we take that kernel and we build it up into a 64-bit kernel. Okay. During the process of converting our 32-bit kernel to a 64-bit kernel, we create the ability to load images, load fonts, we create a terminal system, we create a graphical system, we take the frame buffer from our UEFI bootloader, okay, and we pull that into our kernel so that we can write pixels directly to the screen, okay? Not like in part 1 course where we had text mode. No, that's out the window now. Now we have pixel mode. We can set pixels anywhere on the screen. This opens the opportunity to load images, to create graphical user interfaces, so much, okay? So in module 1 course, we're focusing on taking that 32-bit kernel, converting it to a 64-bit kernel that runs in long mode. We even create the UEFI bootloader in module 1, this module, guys, okay? In module 2 of this part 2 course, we then create the Windows system, okay? We can click and drag windows all around the screen. We create our NVMe driver so that we can load sectors from the SSD disks. Okay, by the end of this course, you will have a 64-bit long mode operating system capable of graph user interfaces. Okay, your programs will have graph user interfaces. You can click and drag them with your mouse. Mouse will be completely implemented. This is a fantastic course. Get it now, 30-day money-back guarantee. .c, csum.o, because we want to link with the csum.o file we just created with the assembler, and then we're just going to say sum. -o sum. Okay, because we need the -o to say that this is the output file. So you can just press enter now. We can see that it's now created that. You can see we still have a warning. You can make that section in the assembly file if it's a problem for you. So here we're going to say /sum, and look what we see. We see sum 50 plus 20 equals 70. So that's how you mix the C and assembly code together, guys, okay? You create a prototype and you don't define a body. So don't do this. Don't define the body, okay? Just like you would in a header file, you just have the reference to it, okay? This explains to C how this function has to be called. So it explains that there's an X integer and a Y integer, okay? During linking, it'll link the address of sum to the reference here on line 8, okay? So it'll resolve the address during linking. So then our sum function will actually call our assembly code here in the csum.asm. Obviously, as you know, we know RDI and RSI are the first two arguments. We add them together, we just return. So then the result will get stored in the result variable in the C function. So that is how you mix assembly and C, guys. It's really that simple.